Um, Hi, Wolf. Um, I guess we run out of time a little bit. Shall I continue for the session 4, if you do not mind?
I think that's the best way to proceed, yeah.
Okay. All right. Um, I guess we can go to technical session 4. Today, the focus of a technical session will be intelligent modeling. Our first speaker will be Haiguang Liao. He is the third year PhD from Carnegie Mellon University, and he is working with Professor Levent Barik Kara. His research focusing on applying machine learning and reinforcement learning for physical design, as well as combinational optimizations. So, Haiguang, are you able to share your screen?
So it seems that it has to be enabled. It's
Um, I actually couldn't. Perhaps, Wolf, are you able to enable Haiguang for sharing the screen? And meanwhile,
Should work now.
Yeah, so meanwhile, for all the audience, and feel free to post your questions in the Zoom chat window, as well as in the Slack forum. Thank you. So Haiguang, I'm able to see your presentation right now. Feel free to start.
Thank you. Thank you, Professor Helen. So hello, everyone. So my name is Haiguang Liao. I'm a third year PhD from Carnegie Mellon University. And so today I'm going to present our work, track assignment detailed routing using attention-based policy model with supervision. So this is a collaborative work between CMU and the Cadence design systems. And so I would like to acknowledge our team and Elias Fallon for his guidance and help with data sets. So about the background, so detailed routing is a very critical step in physical design. And in advanced technologies, the complexity is increasing and makes it significantly challenging for conventional routing method. And we think the key issues include the net sequencing as well as the generalization abilities of the existing routers. So in our prior work, we developed a attention-based reinforcement learning detailed router. And so that works has about 100 times faster than the baseline genetic algorithm-based detailed router. So however, the previous ARL method still suffer from unstable training because it's using policy gradient reinforcement learning. And also it is not able to leverage label data. So based on that, we developed a supervised version of reinforcement learning that adopts the architecture of the attention policy model. And the main contribution here is that first we train the policy model with a supervision based on the label data generated from genetic algorithm. And we also do a comparative study between the supervised reinforcement learning and the previous attention reinforcement learning. So here's the pipelines. So we apply 3 methods, genetic algorithms, supervised reinforcement learning, and the previous attention-based reinforcement learning to focusing on the sequencing the net pairs. And so we are using exactly the same flows, including the track assignment, pin decomposer, as well as the pattern router, so that we have a fair comparison of all these 3 methods. And so some details about the supervised reinforcement learning. So the supervised reinforcement learning leverage the optimized results generated by genetic algorithm. And so given the training problems, the genetic algorithm would first generate results for given problems. So after this, the supervised reinforcement learning is initiated by calculating the KL divergence loss between the distribution based on the genetic algorithm results and the output distribution from the policy model. And then the loss will be used for updating the policy model parameters by backpropagation. And we ran that for 100 epochs. So once the training is complete, the supervised reinforcement learning model is able to provide net sequences for unseen problems for a given design. So to evaluate our method, we try two datasets, which are both sub-6 nanometers technology analog designs. The first is called BIOS-AMP. It consists of comparators and op-amps. And so it consists of less than 100 devices. And the problems are generated by randomly placing the devices to explore the model properties. And the second one is a little bit more complex. So the SAR FSM, it is a sub-circuit of the analog to digital converter and consists of hundreds of devices for each design. And so it's implemented with PyTorch as machine learning framework. And so here are some results. So firstly, we show the correlation analysis between our method and the genetic algorithm. And so in the three data sets studied here, which is shown on each row, on both the training and the test sets, which are on the left and right column, there's like a very strong linear correlations between the supervised reinforcement learning and the genetic algorithm. And the resulting slope and intercepts indicate that the supervised reinforcement learning quality is only slightly lower than the genetic algorithm. And so we also show the results in cost versus runtime fashion of the supervised reinforcement learning and the genetic algorithm on the test sets of the BIOS-AMP dataset and the SAR FSM dataset. So on these two figures, each blue dots corresponding to the results from our supervised reinforcement learning, and each red dots corresponding to the genetic algorithm baseline. And so for both data sets, the supervised reinforcement learning is 2 orders of magnitude faster than the baseline genetic algorithm, while only a slight degradation in the solution quality. And so here are some visualized routing results. So to sum up, so firstly, we propose a novel supervised reinforcement learning approach that leverages supervised learning to train a policy model that is used to solving track assignment detail routing. And the supervised reinforcement learning achieves performance comparable to previous reinforcement learning model and indicate that the supervised learning is a good alternative for training the policy model. And so both the supervised reinforcement learning and the previous attention reinforcement learning model have around 2 orders of magnitude acceleration compared to the baseline GA. And but the supervised reinforcement learning has a unique advantage of learning from past designs or human expert designs. Thanks.
Thanks a lot, Haiguang. There is a question on the Zoom chat windows and from the Zero. I know he's also working on reinforcement learning methodologies. So his question is, with the supervised reinforcement learning, is the reinforcement learning pushed to do better than genetic algorithms, or is just about the speed rather than quality of solutions?
Yeah, I think that's a good question, and actually, as our initial motivation for using supervision is to improve the performance of the reinforcement learning, because we see that there's a gap between the performance, the cost between the reinforcement learning and the genetic algorithm. Yes, that's the initial motivation, but later we find that our reinforcement learning method is very sensitive to the amount of data we are training. So we just improve the model's performance by just improving the size of data sets. And so I would say, so based on our current result, the supervision is basically cannot really just improve the model's performance. So, but instead it is able to push your model to imitate the behaviors of your data sets. Like you might have some specific patterns in your data sets based on past designs. So by using the supervision, you might have better chance to imitate those design patterns.
Okay, but I guess the pushing for the quality of the solution will still be your ultimate goal, correct? It's just
right,
mm-hmm.
right. For sure, yeah.
Okay, so a quick question from Peter Dominski. What are the label you use for supervision?
Okay, so yeah, so for this work, we used the genetic algorithm results as the label. So first we ran the genetic algorithms on all the problems in data sets. So specifically the label would be how the GA sequencing those nets. So it will be a sequence, and we have for each problem we ran the GA multiple times. So it will have a distribution of those sequence, and that will be the label.
All right, then I guess then the following question will be, why did you choose G as the baseline? Have you ever considered comparing with your machine learning techniques to more classical techniques like deterministic optimization algorithms? The question actually from Professor Wolf Schriefman.
Yeah, I think that's a great question. So, and I think the initial motivation is that because we're working with the Cadence Majestic team. So, and one of their existing analog detail router is using the genetic optimization. So we want to improve on that. And the genetic optimization seems to like a fair label because it is performing modestly well. So we just use that. But it'd be very interesting to see how the supervision policy model behaves if we have better label data or like based on exact solvers. Would be probably the next step.
Sure. One more question from Chitrapa Ramesh. He basically asked, and how do you balance between the policy updates from reinforced learning and the policy updates from the supervised learning component?
Okay, yeah. I think the thing we are doing here is like, so basically, so this work is only using supervised, is only using supervision for training the policy model. So we just compare that to the same model trained by reinforced learning laws. So we didn't do this together. So these are pretty much go in parallel. Yeah, so that's okay, yeah.
I see. Thanks a lot for sharing your experience on this, and thanks a lot for answering so many questions. And would you be able to stay with us toward the end of the session in case more questions and discussions come along?
Sure.
Thank you. All right, I guess we can move to the next paper, compact model for initiate MOSFET sizing based on higher order artificial neural networks. Dobroslav, I guess, and you're going to present the paper?
Yes, hi, Helen.
Hi.
Let me see if I can share the screen.
Okay, yeah, we can see that. If you can make it yeah. All right, thank you.
Okay, so my name is Dobroslav Tsonev, and I'm going to present the modeling work that we've conducted with my colleagues Husni and Matthias Schweikardt at Infineon, Germany. So we need device parameters for various design applications that we have, and it's not always easy to get good models for all platforms. For example, if you use simple equations, then obviously you don't get accuracy. And then if you use the complex accurate piecing equations, for example, you are limited to proprietary software such as Cadence, and you cannot use the data across all platforms. Some designers, for example, like to use Python and MATLAB for their applications because they're more suitable for that purpose. So the way we currently solve the problem in a straightforward approach is we supply lookup tables, but the problem with lookup tables is that they basically very quickly grow in terms of storage demands. Even for a handful of input and output parameters, you can quickly get to gigabytes of data requirements for a single device. And then if you have multiple devices, you easily go to tens or hundreds of gigabytes, which is a problem, especially if you have version control systems. So obviously we need some sort of modeling in order to capture and supply this data. So this modeling has to be sophisticated enough to capture nonlinear relationships, which are not straightforward. And also it has to be widely available. So machine learning and specifically neural networks are a very good candidate. So we tried this with straightforward modeling approaches using neural networks, and we had issues with accuracy in general. For example, even in literature, you can find examples where people report very good average error rates, but when you get to the worst cases, you sometimes see intolerable errors. And we had to work a bit on that, and especially in our architecture. So what we did is we came up with 3 tricks. First of all, we included a feature generation layer. And in our case, it was just a simple analytical feature generation layer where you would generate higher order terms from your inputs. In this case, we had 4 inputs, and we came up with 26 features. And these features were generated from the widely known square law equations, where if you expand those equations, you would come up with those features, which typically correlate quite well with your device performance. In this specific case, we were modeling the performance in terms of drain to source current and transconductance. The second part of the network was a neural network with 2 hidden layers with enough degrees of freedom to get a decent fit. Here we also applied a trick, and first of all, what we did is we split the data in 4. Because we had quite a range in terms of output data, where we had small current values and very large current values, as well as for the transconductance. We split the data in 2 for small values and large values, and we further split the data in terms of the operating regions that we were modeling. So part of the data was distributed to the linear region and part to the saturation region. So overall, the data was split in 4, or we trained 4 separate neural networks with the 4 separate data sets. An additional performance improvement that we added was we defined the custom loss function, because in general, the standard loss functions such as mean square error and mean absolute error, they tend to give a lot of weight to larger values. So you get a lot larger errors in the smaller values, but the percent loss function was quite decent. And overall, we got very, very good results in practice. So the average error rates that we have for the whole data set were less than 1%, but even the worst case errors were quite tolerable as well for most of our applications. So the examples I'll give you here are for the worst case. So this is the worst case for our drain to source current. You can see the curves fit quite well on the left, and then you can see the actual percentage errors on the right, where the only more significant errors up to about 15% come from the smallest current values, and these are very close to the threshold voltage for the gate to source voltage, which means that at this point the device is barely on. Similar results we obtained for our transconductance as well. We got very good fit, overall less than 3% for most of the errors, even in the worst case. And then really worst case errors were about 10%, which was quite tolerable and was useful for most of the applications that we would typically have. There are ways to maybe even further improve this work. We already managed to have a lot of storage savings. For example, compared to our lookup tables, we actually require for our neural networks about 1,000 times less storage space, which already made them practical for us. As I said, the error rates were quite tolerable, but we can maybe even improve them further by either improving the feature generation process, or maybe even adding additional modeling for the sub-threshold regions, where you can actually model the data as well and have a smoother transition between sub-threshold and threshold data. Or maybe we can even try more fancy techniques, like for example, trying to model the errors that come out of this current model and capture that with an additional neural network to further dampen the error that we see. Thanks a lot.
Very interesting work. In fact, working on the model for the MOSFET transistors isn't a very easy task. Actually, I'm curious about this generated feature components, and can I take it as a more like pre-processing in general machine learning methodologies to create it in certain features and for the further analyzing?
Yes, basically what we did is we used a simple, straightforward approach because we know that even though for example, the square law equations, they're not accurate for our data that we get nowadays, they still correlate quite well, which means that they are going to suggest features which have a decent prediction capability. And then we let the neural network decide how to exactly combine them and maybe even add some additional fitting on its own.
I see. Thank you. A question from Peter Domsky. Are the used features of the feature generation layer learned or handcrafted?
They are handcrafted. As I said, they're derived from the analytical square law equations. If you take the square law equations, which is the general form here and here, sorry. And then you expand those, you would come up with those features as a suggestion to the network of predictive features. We make no assumption as to what features are actually going to be really predicted. There is an additional possibility for optimization by actually examining all the features individually and trying to remove those that basically don't add too much value to the network.
I see.
But yeah, that would depend on obviously the performance parameter as well, because some features might be useful for the current and some might be useful for the transconductance and so on.
I see. And one more question coming from Helmut Grip, and he asked, I'm wondering how other response surface modeling methods in this application, the neural network, would compare with this.
You mean other modeling other than neural networks?
Yes.
Well, effectively what you can see is the data here was generated in the curves. The data was actually generated from the cadence models because we don't have the raw data. And the cadence models were expecting to be quite accurate. So you can see that the neural network can approximate given the Bayesian models from cadence quite well overall. And maybe in certain cases, it's even beat them if you actually have the raw data.
Actually, from your result, it seems like the model performed pretty well when voltage range is large, but less accurate when, for instance, the VDS is very small.
Yes, basically when you have very small currents and when you have very steep curves as well, it's easy to actually get larger errors. But we would say that for a lot of the applications, this is tolerable. For example, for initial sizing of the devices, then obviously if you want to be really accurate in those regions, it's better to switch to actually more accurate simulations.
Makes sense.
If you are certain in the simulations, yes.
Yes, makes sense. Yeah, thank you. All right, thanks a lot. And I guess we can move on if you do not mind. Would you be, in fact, there's another question, so maybe we can answer this one first.
Okay.
How you have concluded with the AN configuration, like number of the hidden layers?
Well, basically, we do not claim that this is an optimal approach. We based this on, as a basis, we started from what was available in literature, for example, and with 2 hidden layers, there were decent fits on average, for average errors of the model. So basically, we assumed that 2 layers would give us a good fit, and then because we had large errors towards the region boundaries or in certain parts of the model, we have to add these additional stages or additional features and techniques in order to limit that error further.
I see. I see. Thank you so much. So hopefully you can stay with us longer, and if there are more questions that come out, and you may help to answer this.
Sure.
Okay. All right. So let's move on to the third paper, a efficient and flexible learning framework for dynamic power and thermal co-management. Our presenter will be Yuan. He is a master's student at the Zhejiang University, and his research focuses on CPU power management. Yuan, are you able to share? Yeah, we can hear you.
I can share screen, and there's a window. And I try.
Oh, actually, we didn't see your sharing your screen yet.
I can't share my screen. I don't know why.
You cannot share?
Can you try again? I just set you co-host. Please try again.
Oh, okay.
Okay, we are seeing this, and this is in full screen. Feel free to start. Thank you.
Hello, everyone. My name is Yuan Cao. I'm a master student at Zhejiang University. The paper I will be presenting today is titled An Efficient and Flexible Learning Framework for Dynamic Power and Thermal Co-Management. At the era of artificial intelligence and Internet of Things, battery-powered mobile devices are required to perform more sophisticated tasks and constrained power supply. With the continuous scaling and growing power density, power management has been a concerning topic for microprocessors to achieve good energy efficiency. Thus, most CPU vendors actually deploy their own management strategies. For example, Intel Turbo Boost and AMD Sense MI technology. Both technology optimize performance by preciously adjusting the frequency according to the needs of the processor and the temperature. However, such vendor strategies no longer work well for mobile devices. First, power sensitivity. Mobile devices demand frequent power state transition for varying workload. Second, thermal sensitivity. The cooling capability of mobile devices is typically limited. The last is efficiency and flexibility. Power management algorithms need to be light and flexible to facilitate resource constraints on mobile devices. So we proposed a deep reinforcement learning-based dynamic power management framework that incorporates various machine learning models to address the aforementioned issues. The proposed framework has two parts. One is modeling and prediction, and another is controlling. In modeling and prediction, proposed framework predict power, temperature, and future workload through CPU statistics. In controlling, a deep reinforcement learning-based model is employed to select action, and a lightweight Q-table lookup method is used to select voltage frequency pair. Here is the toolchain for the framework. We ran benchmark in System Simulator Gem file and record the runtime information. Then we can obtain power and temperature of the processor through power simulation tool MLCAD and thermal simulator hotspot. We use an ARM Cortex-A72 architecture as the underlying processor platform with 4 voltage and frequency pair as the table shows. We here employ support vector regression to predict workload. The actual workload and predicted workload by SVR are shown in figure. We can see SVR model can achieve high accuracy for heavy workloads. It also averages out the random fluctuations to ensure good stability. Here we can use the processor performance counters to estimate the activity factor of a processor to predict the power. Since the ARM Cortex-A72 core only supports counting 6 performance events at the same time, so we calculate the correlation between power and processor performance events, and are then able to identify the 6 events which are most related to the power modeling. After that, we use multiple linear regression method to set up model. The power prediction result is shown in figure. It can be seen that the predicted power and actual power is in good consistency. The average error of the power model on spec CPU 2006 dataset is about 3%, with a maximum error of about 5%. We use a linear time invariant system to model the thermodynamics, and the KS test is employed to justify the similarity between the proposed model and actual measured data. If the KS test failed, we will update models through latest measured data at the beginning. The average error below about 1%. When temperature is increased, the error increased to about 1.5%. KS test is carried out at 1,500 milliseconds. The maximum error is reduced to about 1.2%. In controlling, we proposed a deep reinforcement learning-based framework as the overall control loop. However, to achieve the desired efficiency and flexibility, we cannot directly employ the widely used Q-learning algorithm for DRL. Q-learning method need discrete state and large Q table, which leads to low performance. Compared to traditional Q-learning method, proposed method transforms the Q table into a function, so can achieve high performance. Our DRL framework is shown in figure. Proposed training employee modified experience replay to store data. Using the execution time, DVFS time, and thermal as the reward, we define an adaptive parameter alpha to improve training effect. We select 9 indicators as input status, which are to have greater impact on power, thermal, and performance. Select the different voltage and frequency pairs as action according to the states of the system. Next is the simulation test result of proposed control method. We compare the proposed method with the other 3 power management methods: on-demand, max-bips, steepest drop. From the figure, we can see proposed method has fewer frequency switching before the processor reaches the thermal limit. Select the lower frequencies at the early stage and therefore reach the thermal limit in a larger amount of time. After the processor is close to the thermal limit, processor is controlled to switch to balance between performance and thermal. Finally, is the performance. The proposed framework finished the benchmark first and achieved performance improvement of 6.8%, 5.3%, and 6.2% when compared to other strategies, on-demand, max bips, and the steepest drop. That's all of my presentation. Thank you.
Thanks a lot for the very nice presentation. So I guess before other people chime in and ask questions, and I kind of wondering for your simulation or the methodology evaluations, and did you use like one applications, or how many applications and did you test it? Because I assume the testing or the data collection of your case will be quite time consuming and not that easy.
We didn't test too much applications because until we read this paper, we don't have enough time to finish other method or more applications. So I think we will finish this better in the future.
I see, I see. Well, this is actually the meaning of this workshops, and I guess, and we kind of encourage some early research outcomes and to share. But I can see that your result is very promising. There's another question actually from Haiguang. He is wondering, how is the action space represented? Is each action corresponds to tuple? A1, A2 corresponds to action on two variables.
Two variables. I think.
Well, in fact, the question is posted on the Slack forum. You may take a look and kind of an answer over there. We can also have your answer at the end of the session. Would that work?
Okay.
Yeah, please and stay with us. Okay, so considering the time, let's move on to next presentation. That will be partial sharing neural networks for multi-target regression on power and performance on embedded memories. Our presenter will be Felix Last. He's a second-year PhD student with Intel and TUM, Technical University at Munich. He has a background in computer science and advanced analytics, and he's working on applications of machine learning in EDA. So Felix, feel free to start.
All right, thank you very much, Helen. Can you see my screen?
Yes, and perfectly.
Okay, great. So hi, everybody. Thanks for the intro. My name is Felix. I'm a PhD student with Intel Germany and also being supervised by Professor Ulf Schlichtmann here at the Technical University of Munich. And today I will be presenting our work on partial sharing neural networks, which we use to perform regression on the power and performance of embedded memories. Now, when we speak about embedded memories, these are rarely designed by hand nowadays. Instead, typically we use so-called memory compilers, which are input set of parameters which describe what kind of memory we want to produce. So most importantly, what we will put in is the size of the bit cell array that we need. And then we have other architectural parameters which describe, for example, whether we should split this bit cell array into multiple banks. Now, once we put this into the compiler will produce a memory. So it will produce the layouts and RTL codes, all of the artifacts that we need to keep working with this memory in our design flow. Also, it tells us an estimate of the PPA that we will achieve with this. And of course, as we've seen in most of the talks here, our goal is to optimize this PPA. Now, to optimize the PPA, we can tune these knobs being the parameters going into the memory compiler, right? So we can play with the number of banks, for example, to change our trade-off between area and performance. But if we wanted to run any kind of optimization to tune these knobs, whenever we want to sample a solution and estimate the PPA, we would have to run this compiler, which runs for around up to 1 hour for each memory. So you can see if we run any type of iterative optimization algorithm, it's just gonna take a lot of time simply because of running the compiler. So our approach is to employ neural networks to estimate the PPA based on the compiler input parameters, with the goal of speeding things up for an optimization algorithm to sample solutions much faster. Now, these neural networks run much faster than the compiler, obviously, and we've also we're confident in their usage, so much so that we actually have them in productive usage at Intel for many years now. Yeah, this is at a large scale. We support very many technology nodes and very many compilers on each of those nodes. But this work really focuses on a new architecture that we try to improve our results. And we saw a question earlier on regression problems in EDA. Well, here we have a typical one. We're trying to predict PPA, and because we're trying to predict all of them simultaneously, or yeah, in parallel, what we look at is a multi-target regression problem. And here's one approach, partial sharing, which is meant to improve multi-target regression. What you can see is a fairly standard neural network, but let's take a look at what's going on in the middle. To understand what's happening, it's easiest if we take away the non-shared layers and we look at the result. What we see is a neural network with shared layers, which are connected to all inputs and to all outputs. So basically, we have one neural network that makes multiple predictions at the same time. On the other hand, if we drop the shared layers, and we're left with only non-shared layers. And these are also connected to all inputs, but each set of non-shared layers is only connected to one target variable. And this is really corresponding to having separate neural networks trained separately and completely unconnected separately for each target. Now, the reason that we want to mix this together is that when they play together, we can use the shared layers to exploit the so-called target-to-target correlations. So that means we can use what we already know about one target to make our prediction for another target better, because we know that our target are somewhat correlated. And we can use the non-shared layers to then fine-tune the predictions for each of these targets and extract the target-specific feature-target correlations. As for the results, we found that this multi-target regression method also helps for our multi-target regression problem. We can see here that from full sharing, which is on the right, so on the right side we see at 100% a network that only has shared layers. We managed to reduce our prediction error by approximately 10% using this partial sharing, which you can see in the middle, 50% of shared layers are shared. It's also noteworthy that it is also better to train this partially shared network versus training multiple networks, one for each target, which is what you see on the very left with 0% sharing. So in both cases, from both baselines, we managed to improve our error, with worst case prediction errors improving as much as 50%. And yeah, with that, I would like to conclude this brief summary and look forward to your questions. You know where to find more info if needed. Thank you.
Thanks a lot for sharing this wonderful work. Actually, Felix, I recall a year ago before a pandemic started, I was in TUM and there were very brief discussion about this, very initial ideas, and it's very glad to see you already made significant progress on this. I actually curious about this and sharing and then sharing components. Can I understand, or basically my question is, does it share similar concept with the transfer learning? Because a lot of the transfer learning techniques and kind of starting with the model trained for certain objectives. And then when it's transferred to another applications, we maintain front layer, but retrain the the last several layers and to be optimized for new application. Can I say that this is actually shares certain contents of this, and when you mitigate to another applications, you might only focus on the new kind of a non-shared part?
Yeah, I think you could see it as somewhat related to transfer learning, because we do try to share knowledge here between multiple targets. I think the difference a little bit is in transfer learning, usually the focus is on starting in one domain and then shifting to a new domain. Whereas we are doing all of this simultaneously, right? We're not training a model for area first and then moving it to predict power later.
I see.
But I think it's interesting that you mentioned transfer learning, because that is something that we really look into right now for reducing how much data we need to train new models. For example, right now, when we get a new compiler version, we have to regenerate data completely from scratch. And our model starts out without any prior knowledge about the application. And we're looking into how we could use previous version data to make the training more accurate and faster for new technologies.
I see, I see. Wow, very interesting. I hope you also have a successful, outcomes on that line as well. Thank you. Yeah. Oh, there's a question before we move on. There's a question from Asman asking, for shared network, does it differ from target to target? And it gets trained from scratch? I mean, the architecture itself.
So the architecture between targets is the same. So we have fully connected non-shared layers for each of these targets. So the prior situation is the same for each target. We use the same network for one compiler, right? So there's nothing that differs here between the targets. And yeah, we train from scratch each time currently. We're trying to start from some kind of prior knowledge that we either have before even generating data or from other compiler versions, but that's not yet being done.
Okay. It seems no more questions. Yeah, go ahead.
Can I ask a question?
Yes.
Okay, this is Meron from University of Bremen. I just have a basically maybe fundamental question that I'm curious to know that what is basically this execution time for the compiler itself to generate this result, and what would be basically the improvement in this case if you compare it with this compiler results using neural network and the compiler.
You mean in how the compiler execution time compares
Exactly.
to the neural network execution time?
Right.
Well, the compiler runs for 30 to 60 minutes each time.
Oh.
And the neural network makes 1,000 predictions in less than a second.
Oh, okay. Just wanted to know, like, the estimation that what would be the difference in this case, because sometimes happen that the difference is not that much. Okay, for example, like the compiler itself is 10 seconds and the neural network is 5 seconds, so it is.
Okay.
Now
no,
like,
it's really massive.
sense.
So
yeah,
especially given the number of memories that we have on today's chips, one product will have up to 1,000 different memories that all need to be optimized. So really executing the compiler multiple times and try and error is very expensive.
Right. Okay. Thanks.
Right.
Thank you.
Right. I think this is a very important point, and particularly for the people like me, perhaps didn't realize the value of this yet. Thanks for bringing up this question. Is there any other questions? Okay, so if no more questions in a moment, and we may move on, Felix. And if you have other questions, then feel free to continue post on the Zoom or the Slack. The last presentation will be about explaining and interpreting machine learning CAD decision, a SC testing case study. And our presenter will be President Krishnamurthy from NYU. I apologize for this.
Thank you for that introduction. Let me see if I can share screen. Oh, it says the host disabled. I guess you want to add as co-host.
1 minute. Okay, I guess, yeah. I guess if you are a co-host now, you should be able to share.
Is my screen visible?
Yes.
Okay, I'm Prashant Krishnamurthy from NYU Tandon School of Engineering. This is joint work with my colleagues at NYU. So the main So as the title of the paper suggests, the main focus in our work in this paper is on trying to develop an explainable and interpretable machine learning framework for multiple CAD problems. And essentially, in terms of interpretability, there are two aspects that we are looking at. One is human readable explanations of the decision logic. And the second is providing context-sensitive explanations for individual input data points. And the basic difference being that in one case, the rules utilized for classification, the other is given a specific data point, explaining why that particular data point was classified the way it is. And specifically for CAD problems, and more particularly in this particular paper for test point insertion as a particular example. And the idea is to provide designers with insight into kind of the black box of machine learning. And that entails a few sub-questions. One is given some data, in this case, for the test point insertion problem, which features in the data were relevant for classification, what combinations of features, like for instance, inequalities among certain features in a context-sensitive way, and given an input data point, what's the best context-sensitive explanation for that particular data point. And the particular approach that we're using for this is called SIFs, which is sentences and feature subsets. And this is a method that we initially developed in the context of cyber networks and intrusion detection, but it also has nice applications to other domains. So this is our initial foray into applying it to a CAD problem. The basic idea in SIFs is that instead of learning kind of like deep models, we learn more of multiple sentences kind of models, wherein it's trading off depth versus breadth in terms of thinking of it like a neural network. So each sentence that SIFs learns is of the form like if a particular condition, then output equal to 1. And the condition is an AND of multiple inequalities. So we call each of these words and the combination of words as a sentence. And each word is basically an inequality among particular features. So it's a sentence and feature subsets in the sense that it's a sentence comprised of words. Each word has a feature subset. And the overall classifier model is an OR of multiple sentences. So if you think of in a high dimensional feature space, each sentence is modeling a sub-volume of the overall volume that corresponds to a particular classification. And of course, the sub-problems in training that include deciding which subsets of features to use in each inequality, what the coefficient should be, and what combinations of inequality should appear in each sentence, and what sentences to use for the overall classifier. And this is a kind of block diagram of the overall methodology. So there are a few different interconnected problems as I was mentioning. So when applied to a particular problem, in this case, the test point insertion, which essentially comes down to given a net list with some nodes which are possibly hard to test in the sense that logic faults at those locations would be difficult to detect with random inputs. Is it possible for a machine learning system to not only indicate that those points are hard to test and therefore would be good candidates for inserting new test points, and also provide context-sensitive human-readable explanations for why those points were picked? So given the node features, in this case, those would be like features drawn from the circuit or the local neighborhoods and so on. I'll have more to say on that in a couple of slides. The question is to basically do some sort of feature augmentations by taking the local context and so on, and then pass it through a sequence of multiple steps which try to address the questions of which features, what combinations, and so on. So in terms of picking the features, it's a multi-level kind of approach, wherein the initial thing is genetic-based approach, wherein random subsets of the features are selected, and the utility of those are judged using a random forest method. So using the feature importances from a random forest to decide which possible subsets are good in a more global context. So given maybe 30 or 40 different features which are drawn from the circuit, which particular features are maybe most relevant. And then once those are picked, then a population of sentences is trained, which is essentially in this form. So you have multiple sentences, each sentence of the structure, wherein it's basically like a condition, which is an inequality among features. Here, Fi are the features, Cijk are the coefficients, Mij are the mask variables, or 0 or 1, indicating whether a feature is used or not. So everything inside this parenthesis is one word. The and of those basically corresponds to an and of words, which is a sentence. The or of multiple sentences corresponds to the output. So training that involves training all of these different constituent stuff. Of course, in terms of neural network kind of training, it's not directly amenable since we have and or and things of the nature, and of course, hard inequalities like this. So one of the important aspects is a differentiable relaxation of this, which replaces the inequalities with sigmoids, the and the or with a product and a max and so on. And then the mask variables are dealt with using a genetic algorithm. The coefficients are dealt with using gradient descent. And once the population of sentences is trained, each of which is like an if a particular condition, then a conclusion holds, the population of sentences is further pruned, and there is some compression methods and so on, which I won't get into the details of it for time reasons. But once those are learned, that becomes a model, which is an or combination of sentences, each sentence being an and combination of inequalities. Now, all of this on top here is the training time. At test time, when a set of node features is given and features are augmented utilizing the local graph in the netlist, the human readable explanations are drawn by utilizing this learned model to see which sentences are activated by the sample, in the sense which of these conditions was satisfied by a particular input sample, and then picking the best one by utilizing the activations. And that forms a classification with the human readable explanation. So in terms of specifics of the particular example we're looking at here of the test point insertion, the idea is that for each node in a circuit netlist, you have two numbers, L0 and L1, which indicate how difficult it is to detect a stuck at 0 fault or a stuck at 1 fault. The training data is generated using ATPG, which is reasonably computationally expensive. So part of the idea of ML, of course, in this problem is to reduce the runtime. But more importantly, what we're looking at is explainability in terms of indicating why something is hard to test, which is something that even with ATPG is not directly available. So we're hoping machine learning in the interpretability context can provide that. And nodes with small L0 or L1 values are hard to test. In fact, the ML task we looked at is detecting nodes which are either low L0, low L1, low L0 and low L1, or low L0 or L1. The last of these is basically that it's either hard to test for a stuck at 0 fault or hard to test for a stuck at 1 fault. And those would be essentially the ones which are most relevant, in the sense for some reason they're hard to test, so they would be good candidates for test point insertion. So in terms of generating the features, the basic features in terms of scope indices and the logic depth, all of which can be extracted in linear time. This set of circuit level features augmented with graph-based features, which are based on local and global proximity in the graph. So for instance, percentages of primary inputs and primary outputs connected to a node, minimum path lengths, the number of paths to primary inputs and outputs, the fan outs at each node, the mean, max, and min of the scope metrics with immediate predecessors and successors. So it's like a augmentation based on a temporal, based on a local neighborhood of each node. And the total feature vector becomes a length 36 for each node. So to evaluate the methodology, we use a few standard benchmark data sets from ISCUS and EPFL. And from the 20 circuits we consider, we use 15 for training, 5 for testing. There's an important point here in the sense we don't take a large circuit and use part of it for training, part of it for testing, since we don't want to learn something specific to a particular circuit, like some sort of things which are very specific, but something which is more physically realistic in terms of rules for detecting hard to test and so on. So it's based on just using completely separate circuits for training and testing. So in terms of quick snapshot of results, so two types of results we want to look at. One is the accuracy of the machine learning, and the other is the human interpretability of what is actually predicted. So in terms of accuracy, when we look at the 4 different machine learning tasks, the low L0, low L1, low L0 and low L1, or low L0 or low L1. Again, the and means that it's a node at which it's hard to detect stuck at 0 faults and hard to detect stuck at 1 faults. The or indicates one of the 2 types of faults are hard to detect. So we get reasonably good accuracy, precision, recall, and F1 scores for the or, which is the most relevant since it's just any type of hard to test kind of nodes. We get an F1 score up to 0.971, and which indicates that if the machine learning model indicates that a node is hard to test, those would probably be pretty good candidates for test point insertion. And again, the ground truth for evaluating this is based on the computationally expensive ATPG computations. and the machine learning model runs in a very, very tiny fraction of the amount of time. It's probably something around more than 100 times faster than running the ATPG. And of course, it goes with the size of circuit as well. The machine learning model scales close to linear, whereas the ATPG can go up much faster than linear. And in terms of the other question, wherein given the confidence of each sentence in terms of activation of the sentence, the question is, if something is marked with high confidence as hard to test, is it really hard to test? And for that reason, we did a correlation study here, which is if indeed the top few ranked hard to test nodes are actually hard to test based on the ATPG ground truth, then we would get this black diagonal line indicating, for instance, the top 40 ranked ones are indeed 40 hard to test. So while some of these plots, these are for the low L0 being the red dots, low L1 is the blue dots, low L0 and low L1 are the green, and the low L0 or low L1 is the pink dots here. We see that the low L0 or low L1 practically perfectly tracks the hard to test line, which means that indeed if something is marked as hard to test by machine learning classifier, with very, very high likelihood it's actually hard to test. And there's a strong correlation between the classifier confidence values and the actual test difficulty of testing. So now in terms of the human readability, for each node, when it marks it as difficult to test either for logic 0 or logic 1, in terms of detecting stuck at 0 or stuck at 1 faults, it generates a sentence. So again, these are the words wherein each word is an inequality in a subset of features. So the overall SIFS model is basically sentences in feature subsets. So each sentence is an AND of multiple words. Each word is an inequality in terms of subset of features. The overall set of features were 36, but here, for instance, for a particular node, it picks 4 features and says that due to these reasons among these 4 features, this particular node was marked as low testable for logic 0. Another node which was marked as low testable for logic 0 and logic 1, that's the generated sentence, wherein these are particular features that were utilized to contextually mark that particular node. And there are a couple of things that are useful here for the designer. One is even the highlighting of which particular features were used could already be actionable information, because it says that that particular node had a low control observability index. So here the CO is the scope observability index, CC is the scope controllability index for logic 1. So it marks that particular characteristics among those is what indicated that this was low testable. So that could already give an information in terms of deciding what to do about it. Plus the additional information in terms of what inequalities were satisfied also indicates how useful it is to maybe bump up one of these versus the other one based on the coefficients. There's more discussion in the paper in terms of why these particular features make physical sense and so on, but in the interest of time, I'll skip over that. So in conclusion, this we consider as like an initial foray in terms of applying this particular kind of interpretable machine learning for CAD problems. And the concept in a flowchart is like this, wherein if we think of the design as a iterative approach, wherein we have the design being done, and then a machine learning model is utilized to generate predictions, and then we have design decisions. The typical flow is that the human designer has to look at the predicted stuff, make some design choice and run it again, and then see whether it had a benefit or not. Whereas if there's an explanation being provided, there's a lot more actionable information, since there is more contextual knowledge as to why something was predicted the way it was by the machine learning model. And by utilizing that, the design decision can be a lot more informed. And the idea is that the overall closed loop design process can become a lot more effective, and maybe fewer design iterations and much more targeted design refinements during the closed loop design process. And again, the method tries to highlight the important features, explain the classifier logic, and provide context-sensitive explanations. So I'll stop at this point, and be happy to take any questions if there are.
Sure. Oh, very interesting work, especially this an explanation and interpretation part is very interesting. I our audience and have a question. Dr. Mark Shen asked, how is this method compared to XGBoost with same set of features and also graph-based learning models published before?
Yeah, so thank you for the question. So there are actually a few types of machine learning which date back actually all the way to probably 1960s in terms of decision trees and combinations of decision trees and boosting based methods, XGBoost and things like that. So a couple of differences in this approach. The biggest one is that when you look at the conditions that are being generated, they are multi-feature. So typically, most decision tree methods structure the decisions as a sequence of single feature tests. So it's like if F1 is greater than something and F2 less than something and so on. So if you think of it in the feature space, it's like fitting the decision volume based on axis aligned boundaries. So you have tests on single features, whereas here you can have a lot more flexible tests wherein any word can involve any subset of features, and the set of features is picked as part of the training procedure along with the coefficients for that. So you can essentially fit any oblique boundaries in decision space, so you can generate much more compact sentences. So in terms of page limits, we're not able to include those details in this paper, but in terms of other domains that we applied this to, we found that often the number of like decision tests that are required in decision tree kind of methods can go into like 30 or 40 tests, wherein we can often generate something with 2 or 3 tests in this approach. So of course, depending on the particular data set, depending on the particular topology in feature space, the details could differ, but that's one big advantage in terms of being able to utilize multiple features, and the choice of features is part of the training procedure. Did that answer your question? And I think there was a second part of the question, which I probably
the second part. The second
Oh, in
part
terms of
was
graph.
that graph.
Yeah. So in terms of graph methods, the accuracy that one can generate can actually be very good, but in terms of interpretability, it's not, at least in terms of type of interpretability we're trying to generate here, it's not particularly more interpretable than other neural network methods, in the sense that you still have like graph convolutions and so on. So you pull in features from the neighboring ones and then aggregate over farther and farther distances, for example, using graph convolutions. And once the result is generated, the designer cannot necessarily go back and interrogate exactly which features and why that particular data point was marked the way it is. So in terms of generating contextual explanations, we feel that this can provide some advantages.
I see. I actually shared the confusion with Asma. He asked about the opportunity for this an explanation part. Is it a trainable part of the machine learning methodologies? He said that, I mean, these weights you use to calculate conditions, are they trained or they come from the originally trained model and calculated as a mathematical formula post prediction?
So the SIFS model generates a population of sentences. So the multi-sentence model is what is being trained. So it initially starts with a set of flat features in a sense, and then the feature set is down selected as a first step, and then the set of sentences is trained, wherein each sentence is of this form with multiple words and so on. Once the training is done, then the set of sentences is fixed, but there could be many sentences which you can visualize as if you have a high dimensional feature space and decision volume inside that, which is fairly amorphous with even maybe discontinuous and so disjoint subsets within that feature space and so on. Each sentence is modeling a sub-volume of the feature space corresponding to the output equal to 1, whatever be the classification task. And given a particular input data point at inference time, what is done is picking the best sentence which explains why that particular input was classified the way it is. So the population of sentences is trained during the training time. So the coefficients, all of these things are fixed once the training is done. But at inference, what is done is to choose among the sentences which one is the best explanation. So if you were to think of a feature space and multiple disjoint parts, and in this context, a node could be hard to test because of many different disjoint reasons. And essentially, at the inference time, it picks the best sentence, indicating the best contextual explanation for that particular input data point.
Actually, I never working on this particular cases, but I've been working on language model before. I kind of curious, and when you pick the best sentences and versus perhaps in several best sentences, is there any big discrepancies, and would that kind of offer more explanation, useful explanation? I mean, yeah.
Yeah. So there are a couple of things that are done when picking the best sentence. Now, of course, the definition of best comes down to a few different things. One would want the highest activation for that particular input data point. One would want the most compact sentence. And one would want the sentence which is the most generalizable in the sense it covers as much of the training data as possible. So the definition of best is actually a weighted average of all of those, in the sense that we look at the activation for a sentence, and then that gives kind of like the baseline saying this is, maybe it was activation of 0.9 out of 1. And then we say, okay, even if something is 0.7, that still could be a valid explanation for the data point. So taking everything from like 0.9 to 0.9 minus epsilon, let's say until 0.7, all the sentences in that population can be thought of as explaining the data point. Then among those, we decide which is the best by looking at their compactness and their performance in the training data. So in a sense, it's a sentence which is the most compact and was most generalizable based on the training data, and also activates with a high activation level for that particular input data point. Now, of course, within that space, there's quite a lot of tuning parameters that are possible. And as you're mentioning, it's also possible to pick multiple sentences. So you can pick not just one best sentence, but also maybe like top 5 sentences. So there are other contexts in which we've been looking at that. And that's probably also going to yield some fairly interesting benefits, wherein the human designer could be provided with multiple explanations saying this particular classification is because of these 5 different reasons. And some of those might not be directly actionable. And as I was mentioning, also some of this work we initially developed in the context of network security for cyber detection, intrusion detection, and so on. And in that context, some of the explanations might not be directly actionable. It might indicate something intrinsic to the network, whereas something else might point to maybe reconfiguring a firewall and things like that. So when the top few sentences are presented, the human can then decide which of those is the best from the human point of view as well. And of course, then one can pose a meta-learning problem wherein based on the human operator's feedback as to which one is best, then you kind of learn a model as to which of the sentences is best. So there's a lot of open-ended things. So in a sense, this is kind of our initial foray into applying this to a CAD problem, but hoping that there's more stuff that can be done based on that.
Definitely, definitely. I think this is very, very interesting. Well, we kind of run out the time. Just in case, and there are more questions and coming out, and please and keep an eye on our Zoom meeting and also the Slack forum.
Sure.
So before I really move on, I guess and there's some leftover questions into Yuan. Yuan, would you like to take 1 minute to answer that question?
Yes, yes. Can you hear me?
Yeah, we can.
For this question, I think action
So
space.
let me just recall a little bit. The question was, and how is the action space and represented? Is each action corresponds to a tuple? Please go ahead, Yan.
I think the action space of our deep reinforcement framework is the frequency and the voltage pair that the processor can choose. And current frequency and the voltage are in the state of our framework. I don't know if the frequency and the voltage pair is tuple. In Linux driver, the frequency and the voltage pair is is called operation point. That's
Okay.
all.
Sure, thank you. Thanks a lot. I guess and there's still a lot of things to explore on this in space. But I'm very happy you are able to be with us and sharing your preliminary study results. And thank you. We kind of really ran out of time for the sessions. I'd like to thank all our speakers and for being with us today. And I hope you know, this is a pleasant experiences and we can continue doing this. So now I will pass, you know, the control to Raviv.